So here is the inverse trig functions recap. The idea of inverse trig functions are actually fairly, reasonable types of things to ask. Inverse trig functions are what allows you to figure out what the angle is in a triangle like this. If you have a triangle and you know what two of the sides are, and you want to know what that angle is, I've never tried to do this in my real life, but I feel like this is a reasonable thing that somebody might want to do. The way to do it is using an inverse trig function. And the idea here is looking at this triangle, you have to decide for yourself if you want to use a sine, a cosine, or a tangent. But in this case, I'm going to use a tan because the two sides that I know about are the opposite and the adjacent. And I remember, because I'm a good boy, that's what the tangent is about, the opposite and the adjacent. So tan theta is opposite over adjacent, which in this picture is 4/10. Since I'm going to use my calculator, I might as well write it as 0.4. And then to solve for theta, theta is the inverse tan of 0.4. This is sometimes called the arctangent. That's just a synonym. It means the same thing, and sometimes people write it out, arctan. That means the same as tan with the little -1. And then this is something you can just plug into your calculator if you really wanted to find that angle. I did this one in my calculator. You have to be careful about the degrees and radians. This is 0.38 radians, but if you put it in degree mode, if you're interested, 21.8 degrees, which seems reasonable, I guess, based on the picture. I mean, this is not a very exact picture, but that's what the inverse trig functions are meant to be used for. All right. What we discussed was, I got two types of things that you should know how to do based on what I had you watch. How about this one? Simplify inverse tan of sine of x. This can actually be simplified so that no trig functions or inverse trig functions remain. It's some combination of x squareds and whatevers. How do we do this? I would first of all draw, sorry, I meant to write it the other way around. Tan of inverse sine. Would you mind if I just move the little guys around? That's what I meant. Tan of inverse sine. I actually don't know. I suppose you could do inverse tan of sine x, but that's actually, I'm not into that. I don't want to talk about that. Tan of inverse sine of x. All right. How do we figure this? First of all, I would think of this inverse sine of x right there. This means the angle whose sine equals x, right? So I would think of that, at least temporarily, as theta. And then what does theta look like? Well, sine of theta is supposed to be x. That's what inverse sine of x means. If inverse sine of x, I'm calling theta, that means that sine of theta is supposed to be x, because this is the inverse of the sine. And then x, of course, I want to think of this as the op over the height. That's what the sine is. And just so that it looks like a fraction, I'm going to write x as x over 1. So this right here is theta, and then I am going to draw. Opposite is x, hypotenuse is 1, like that. This is the setup. You have to just draw a little triangle. All right. And now I want to find the tan of that angle. The tan is opposite over adjacent. Now I don't know what the adjacent is, but actually you can figure out the adjacent by doing the Pythagorean theorem. So the Pythagorean theorem, if I call that a, the Pythagorean theorem says 1 equals a squared plus x squared, and then we can solve for a in terms of x. So I would subtract the x squared and then take a square root. A is square root 1 minus x squared. So that's what a is. And now, finally, we can say what the tan of theta is. It's the opposite over the adjacent right here, and that's just purely in terms of x. So this will be my answer. Tan of inverse sine of x is tan of this theta that I was talking about, but looking at the triangle, it is x over root 1 minus x squared. There you go. So you can always simplify any kind of inverse trig function inside of a trig function. You can always draw the triangle and do this stuff and re-simplify the answer. All right? So that was one thing that I wanted you to know how to do. And then also, you should know the derivatives of inverse sine and inverse cosine. I went through a little derivation in the video, which I don't necessarily expect you to remember how to do, although it's actually not very different from what I just did up there. This is the formula anyway. The derivative of inverse sine is that. The derivative of inverse cosine is the same thing but negative. Like so. The same thing but with a minus sign. These are the derivatives of inverse sine and inverse cosine. All right. Maybe just to get us going, I had a few little examples for you all to try. How about find the derivative? This is just a little sort of a chain rule kind of a thing. See what you think. And the last one is not a derivative, just resimplify that so that it doesn't have any trig functions in it. Similar to that first thing that I did. See what you think. Chat with your friends. I'll come around and see how you're doing. Yeah, but it, would it be x? Right, x squared. Okay. How's it going? So for this derivative, yeah, you have to use that. Yeah, so this, use this formula, but you use root x instead of x. Okay here? Yeah, that's good. That's pretty good. How's it going? No, that one you are not doing the derivative. How's it going here? It's looking pretty good. Yeah.
I just thought that one was also fun.
Yeah. We could find it. Looks like folks are doing fine. Let's chat about them. I know most people aren't finished yet. That's okay. The first one there should be, you use the formula, in the box up here, but I'm using root x instead of x. So I'm going to have to do the chain rule. So it's going to be 1 over square root 1 minus here root x squared. That's this little piece of it is just x. So that was just plugging into the formula in the box using root x instead of x. And then because I had root x instead of x, I have to do the chain rule. So it's times. Now the derivative of root x I think of as 1/2 x to the 1/2. So the derivative of that is 1/2 x to the minus half. I think that's what we got. If you want to simplify a little bit, that root x squared on the inside there can be just x. But you can't really do much else with that. All right? Okay. And this one here, 5x squared times inverse cosine x. That is a product rule. You got to do the first thing times derivative of inverse cosine is that formula up there. Minus 1 over root 1 minus x squared. That was the first half of the product rule, and now it's the second thing, inverse cosine x times derivative of the first thing would be 10x. That's a product rule. That's the third time we did the product rule today. Amazing. All right, and then the last one. This is, I'm not asking about a derivative here. I just want you to simplify that, and you should do it similarly to this business that I did up here. You can see the format is pretty much the same. It's just cosine and an inverse tan. So I start off by thinking of this inside thing as an angle theta, and it is a theta where the tan of that is 3x over 5. The tan is opposite over adjacent, and so I put 3x here and 5 here. This is now an angle where the tan is 3x over 5. And I intend to take the cosine of that angle. That's the adjacent over the hypotenuse. So we have to find the hypotenuse here. And again, we use the Pythagorean theorem. So if this I call c squared is 5 squared plus 3x squared. So this is, to solve for c, you have to use the square root. 5 squared is 25. 3x squared is 9x squared. All right? And you cannot simplify that. That's just what it is. Don't take the square of each part there. All right? So that's the c. Root 25 plus 9x squared. And then the tan, no, I want the cosine of that, which is 5 over this c business. So cosine of inverse tan 3x over 5 is the adjacent over that hypotenuse, which is 5 over this guy. I hope you got something like that. Any questions about that? This is a slightly weird kind of a thing to do, and as you know, I'm like in general, I'm not really big on simplifying things, but actually I'm kind of emphasizing this because this is going to be an important step in some of the weird integral tricks that we do later on, they require you to do this kind of a thing. So this is something that's going to come up again in the future. It's not really hard, but you have to, there's a few steps to it. All right. Excellent. Here ends the recap. I wanted to talk a little bit about the inverse tan, because at least of the parts of the videos that I asked you to watch, I actually didn't talk about the inverse tan very much. So let's say a little bit about inverse tan, and then we can talk about integrals involving these things. All of this has been about derivatives, but not about integrals. So let's talk about actually the arctangent, or the inverse tan, is the nicest one of these. If you watch the other videos, you will recall that, maybe I'll just refresh our memory, the graph, say, of the inverse sine looks like this, and it just kind of stops in the middle of nowhere, right? And the graph of the inverse cosine looks similar. It's usually drawn sort of moved over a bit. But this is not inverse tan. Sorry if this is confusing the way I wrote it in my notes. This is the inverse sine. Did I write it?
It's not the inverse cosine.
Yeah, I wrote it upside down. I meant, sorry, thank you. I meant this. I meant this. Yes. I think it's that. Anyway, I'm not trying to talk about that. All I want to remind you of is that this is just a little piece of it. Why don't we get the whole thing? Why do we have to end the graph right there? It's because if we had wanted to continue the graph, because I'm trying to write the inverse of sine, it would have to go back like that, because that's the shape of the original picture, and I'm taking the inverse. But that's not a function anymore, because now like you can see two values for the same, two y values from the same x value. That's why you have to just stop there. Somebody told me I did it wrong. Was it you? You deserve. Sorry if is it demeaning for me to throw candy because you say something that I like? No. We're all friends here, right? Okay, anyway, this is a pain. The fact that the arc sine, this is the inverse sine, it's only like a little piece of a function, and you just can't get any more than that. And this is a little, it's a little sort of upsetting for abstract reasons, and it makes the inverse sine kind of a pain to work with. And people say things like, it's not really the true inverse, it's just like a little piece of the inverse, and the rest of the inverse doesn't really exist as a function. But the inverse tan is actually much better. The reason is, let's just draw a graph of tan, like without the inverse. As far as the trig functions, actually, the tangent is the one with the weirdest graph. The tangent itself has a graph which is a pain to work with. It looks like this, where these asymptotes are at pi over 2 and minus pi over 2. And then those asymptotes repeat. There's like infinitely many vertical asymptotes, all right? This is a real pain to work with, but when we invert this, it actually looks great. So when we invert this, and now we are going to invert the piece in the middle. You can't invert the entire thing, again, because of sort of horizontal, vertical line test considerations. But if I only consider the one in the middle, actually this is a function which goes up to infinity for y and down to minus infinity down here. And so when I invert it, that is to say I'm going to reflect it by 45 degrees into the x-axis. It looks like a very nice function which actually is defined for all values of x. It looks like this, where this is now a horizontal asymptote. This is at pi over 2 and negative pi over 2. And this is the arctan function, also written tan with a little minus 1. I think our book, and I usually am going to write it with a little minus 1, but they mean the same thing. Unfortunately, it is a little confusing. Writing with the -1 might make you think that this is 1 over tangent. It's not 1 over tangent. It's something completely different. All right? This is the arctangent function. And what's nice, why I said this one is the nicest one, it's because this actually is a function which isn't like cut up into pieces. It straight up is a function where you can plug any x value into this. So the domain here is all real numbers. That's what makes it nice. Minus infinity to infinity. And it doesn't just like stop at a certain point somewhere, right? It is a full-on function of the real numbers. It's true the range is not all real numbers. The range is only that interval there, right? The range is the open interval minus pi over 2 to pi over 2. But that's fine. Like I don't really mind that the range is not all real numbers. The fact that the domain is all real numbers makes this really much more convenient to work with than the other two. And it turns out the various formulas for the derivatives and such turn out to be nicer. So I will say similar, I don't think we need to go through the derivation of this, similar to the inverse sine and the inverse cosine x, we can find the derivative by doing an implicit derivative. I'll just tell you what you get. It is the derivative of inverse tan is 1 over 1 plus x squared. This is a nicer formula because it doesn't have the square root in it. The square root, I mean, in the sine and cosine case, it has that square root in it, which is sometimes a pain to deal with. But this one, turns out it doesn't. It's because basically, in order to do this, you make a triangle here. And if you're dealing with sines and cosines, you have to take a square root of something to find the hypotenuse. If you're dealing with the tangent doesn't involve the hypotenuse, so that's why you do not require a square root in when working with the inverse tan. It's just all around a little nicer than the other one. All right. So we can do simple things, much like the examples that we just did. I don't think we need to belabor it. So we can do things like, what's the derivative of inverse tan of 5x squared? This we would do using the chain rule. So I would use the formula as is, using 5x squared instead of x. 1 over 1 plus 5x squared, like that. That's just plugging in directly to the formula. And then I gotta multiply, what do we multiply by? Yeah, the derivative of the inside. Derivative of 5x squared is 10x. There we go. I was going to throw another candy, but like 4 people said it all at once. Sorry. You all lose. I don't know who said it anyway. Better luck next time. All right. That's that. Of course, you could simplify this a bit if you wanted to. I don't care about that. All right. Great. Let's talk about integrals then. So together with these various derivative formulas, we get integral formulas. I will just write this one again. Derivative of inverse sine is 1 over square root 1 minus x squared. This you can write the other way around as an integral. So that means integral 1 over square root 1 minus x squared dx. This is inverse sine of x plus c. All right? Actually, we don't know what the integral of inverse sine is. That's something completely different. But this at least tells us what the integral of 1 over square root 1 minus x squared. This is kind of an obscure integral. I mean, I don't know how many times in your life have you wanted to do this integral, but the answer is that. And actually, this does come up in reasonable situations that we're going to talk about later on. So we actually will be using this in the future of the course. And then, okay, there's a similar one for cosine, but actually it's more or less the same. The only difference, remember, the derivative of cosine has a negative sign here. But if you had a negative sign inside the integral, you might as well just pull it out of the integral and then use this formula instead. So actually, there is one which involves the inverse cosine, but it's just the same with a minus sign, and it's never required, so we're not even going to talk about that. The tan one, though, is worth discussing. That's the derivative formula. It translates into this integration formula. Right. No square root down here, and it's a plus rather than a minus that we had over there. Yeah.
You got a situation where it was like 1 over x squared plus 1. Could you also do that, I guess?
Yeah, x squared plus 1 is the same as 1 plus x squared, right? Although other kinds of variations you should be concerned about. Like what if it's 1 minus x squared but doesn't have the square root? Then you're screwed, basically. I mean, there are some variations of these that can work, but actually that's what I wanted to talk about next. But yeah. All right. How about let's just try a cute little example here. So if I wanted to do, of course you can do these with definite integrals. How about the definite integral from 0 to 1 of 1 over 1 plus x squared dx? Just to make sure you're feeling good about the inverse trig functions. What's the integral? Well, that integral is exactly inverse tan of x. So I would do, this is inverse tan of x, and I have to plug in 0 and 1. Inverse tan of 1 minus inverse tan of 0. What are those? You could do these on your calculator, but actually these ones you don't need a calculator, and I would expect you to be able to do these on one of our quizzes or something. Anybody know inverse tan of 1? This means what is the angle whose tan is 1? Any trigonometry masters out there?
Pi over 4.
I think it's pi over 4. Yeah, this means the angle whose tan is 1. Now, I don't know how you have your various tans memorized, but the way that I think of pi over 4 is a 45-degree angle. It represents this triangle, and that the tan is 1. The opposite over adjacent is 1 over 1. So you should be able to recognize various inverse trig functions like that. You weren't? Ooh.
Thank you.
All right. And then how about inverse tan of 0? What is the angle whose tan is 0?
0.
You know? 0. Somebody said it, but I called on her. Oh, sorry. That's my B. My fault. Go outside. All right. So that's 0. Inverse tan of 0 is 0. That's because the tangent of 0 is 0. And so the inverse tangent of 0 is 0. All right. My answer is pi over 4. All right. This is a very strange integral in my opinion. Like just because you started with something that seems very ordinary looking, like kind of like a polynomial, but the answer ends up involving pi somehow. I don't know if that's kind of surprising in my opinion. Strange but true. Weird result there. All right, let's talk about some tricks. There are some tricks that you can do for variations of those two things. Like I said before, and like he said too, these are very specific forms of integrals. Unless it just looks exactly like that, you're probably not going to be able to use it. Like we used this one, but that's because I gave you exactly that function. Actually, there are some kinds of tricks that you can play. So here are some tricks for similar kinds of, I'll say similar forms. Sometimes your integral will look not exactly like those, but close enough that you can still make it work. So let's try that. So this looks like inverse tan, except the number there in the denominator, that number is supposed to be 1, but here it's not. It's 16 instead. Anybody have a suggestion what we can do?
X equals 4 tangent theta. And then plug that in.
This is fancier than I had in mind. 4 tan theta. I think that will work, but I don't want to think of it in that way because that doesn't use the inverse trig function. Anyone have a more pedestrian idea, perhaps? He's using some knowledge. I'm not into that. No, I am into that in general, but we can actually do this without knowing some fancier tricks. I really would like that 16 to be a 1 instead. Is there anything we can do to just make it so? Yeah? U substitution is kind of a good idea, although that is not going to turn a 16 into a 1. I want a 1 to be here, yeah? Divide everything by 16. I like this idea. It's the last one. Oh no. All right. Divide everything by 16, he says. I'm going to write this as if I am pulling 16 out of that fraction, like so. Just pulling 16 out of the denominator, and then what remains on the inside, that what used to be 16 is now going to be a 1. Now it screws up the x squared part, but we'll handle that later. It's like that, right? We factored a 16 out of the bottom. It turned the 16 into a 1, which is what I wanted. Now it messed up the other part, but actually this other part, hopefully we can work with. 1 over 16, that can just come out of the integral entirely. So that is not going to bother us anymore. Anybody want to recommend what? I want to rewrite this very slightly. X squared over 16. The point is, I want it to look like this, right? 1 on top, 1 plus something squared. Can we make that say 1 plus something squared on the bottom?
Have the 16 go to 4 squared, and then you can make everything squared inside of that.
Yeah, right. You kind of absorb the 16 into the squaring like this. So this is the trick. You divide out by something to force it to be a 1 in front. And then the other part, you sort of suck the constant into the square. And what's the point of all that? Now we can do the u substitution. U equals x over 4. And then this will just say 1 over 1 plus u squared. And that's an arctan of u. That's the idea, where we're going with this. We have to do the du thing. The du will be 1/4 dx. And then I'll move the 4 across like I do. 4 du equals dx. Right? So we get 1 over 16 in the front, integral 1 over 1 plus u. And then dx is 4 du. Sorry, u squared on the bottom. That's important. It better be u squared, because I need it to match the inverse tan formula. All right, then factor the 4 out, and you can do the integral. So actually, when I factor the 4, it'll be just 1/4 outside. 1 over 1 plus u squared du, and that is inverse tan of u. And then finally, put the original variable of x back in. So it's 1/4 inverse tan x over 4 plus c. All right, that's how we do it. It's a fairly simple trick, although it's not obvious, I would say. But you know, once you know what to do, there's not a whole. You gotta make sure all the details work out. All right. Okay, one more simple trick. This one, actually, I think I meant to do this one first. How about that? 1 over square root 1 plus 4x squared. Yeah, I meant to do this one first because it doesn't, it's the same idea, only it doesn't involve the first step. Any thoughts about how we can rewrite this? Sorry, I meant minus inside there. It doesn't work at all with a plus. That plus just totally ruins the whole thing. With a minus is much better. Yeah?
Change it to root 1 minus 2x squared.
Right. Put the 4 inside of the squaring. Root 1 minus 2x squared, like that. And now this looks like the inverse sine formula, which had 1 over square root 1 minus x squared. So we're going to do the u substitution here. U equals 2x. Du is 2 dx. So 1/2 du is dx. Sorry, I forgot to write my dx. All right, so it's integral 1 over 1 square root 1 minus u squared times 1/2 du. pull the 1/2 out, and then it just looks like an inverse sine of u. Right? These are simple tricks to make the formula match what you want. So up here, what we started with had this sort of extra 4 in it. We suck the 4 inside of the squaring, and then it turns into this. And this, the integral, is inverse sine of u. That's the idea. And then at the end, I should replace the original variable. 1/2 inverse sine of 2x. That's how it's done. All right, simple little tricks. Any thoughts about those ones? You will have some practice with these on the homeworks. All right. I think that's all I wanted to say about the inverse trig functions. Right? Great. Let's discuss the next thing, I guess. This is the end of inverse trig functions. This whole chapter in the book, chapter 6, is all about inverses of various things. So we had the logs and the exponential functions, which are inverses of one another, and then the inverse trig functions, which are inverses, kind of. At least they're like pieces of inverses. And then, actually, for reasons that I don't fully understand, I guess it just doesn't go anywhere else. The last section in chapter 6 is about something you may have seen before. It is about L'Hopital's rule, which, as far as I know, doesn't have anything to do with inverses. But they put it in the rule. They put it in the chapter about inverses. I think just, like I said, it doesn't really go anywhere else. But this is a trick for finding limits. It's a little strange, typically when you learn calculus, you talk about limits for a long time, and then you talk about derivatives. And then by the time you talk about derivatives, you don't care about limits anymore. But actually, this is a trick using derivatives which can help you calculate limits. A trick using derivatives to find certain limits. And in particular, the certain limits, this is for, I would say, it's used for when, this strategy, we haven't really done that in this course, but when I ask you to find a limit of something or other, like if I said, what's the, this is just a little sidebar, what's the limit as x goes to 3 of 2x? Your gut reaction should be, I just plug the number in, plug in x equals 3 and see what you get. The answer is 2 times 3, which is 6, and you just say the answer is 6. Usually, when you do a limit, the way you do it is just by plugging the number in and seeing what happens, right? L'Hopital's rule is used. It's a trick for derivatives to find certain limits. It's used for when you plug in the number, but when you do that, you get 0 over 0, all right? I'm sure you recall from doing limits that when you do get 0 over 0, that doesn't mean the answer is 0. And it also doesn't mean you cancel, anything divided by itself is 1, so maybe 0 over 0 equals 1. That's also not true. This just doesn't mean anything. So when you get 0 over 0, it's not even a number. I mean, there's no such thing as 0 divided by 0. This is called an indeterminate form. Indeterminate form. It's not even a number, it's a form. It's like a thing, you can write this down. It just doesn't mean anything. It is indeterminate. It doesn't mean 0, it doesn't mean 1, it doesn't mean anything specific. It's called an indeterminate form. And what what your high school teacher says is it means you need to go back and simplify something or factor and cancel something or something like that. It means you need to find the limit by some other means. You need to work harder to find the limit. All right? Now, when you first learned about limits, you didn't know L'Hopital's rule. But actually, L'Hopital's rule can be used in many of those situations when your teacher had told you you gotta factor. Like, for example, if it's something like lim x goes to 1, x squared plus 2x minus 3 over x squared minus 3x plus 2, right? What you should do to find this limit, you should just plug in x equals 1 and see what happens. I get 1 squared plus 2 times 1 minus 3 over 1 squared minus 3 times 1 plus 2. Now, if you're a fella like me who doesn't like simplifying things, you might be tempted to just leave this as your answer. Drop the mic. But actually, if you look carefully here, you will notice that this is 1 plus 2 minus 3 over 1 minus 3 plus 2. That's 0 over 0. So this actually is not an answer. It means you got to do some more work at the beginning. What would you do to actually get the answer here? Yeah?
Take the derivative on the top and the bottom.
Don't say L'Hopital's rule. You can actually do this one without using L'Hopital's rule. Yeah, you would go back and factor. This is what your baby's first calculus lesson would have told you. Go back and factor at the beginning and then cancel some things and then try again. So this one you would factor as x plus 3, x minus 1. And down here, x minus 2, x minus 1, right? And magically those guys will cancel. And now you can plug the number in. You get 1 plus 3 over 1 minus 2. 4 over negative 1. So the true answer is negative 4, all right? I'm just trying to demonstrate that, like, when you get 0 over 0, this is no indication at all of what the true answer is. Who would have known the answer actually is negative 4 from 0 over 0? You can't get any information from this, and it may even be that the answer is the limit does not exist. Or maybe the limit really does equal 0, all right? Anyway, instead of this, you can use L'Hopital's rule, and it's actually much easier. So you can do this factoring, but instead of the factoring, you do the L'Hopital rule. Apparently, when you spell this, if you write with the little hat on the O, the circumflex, that's the appropriate way to spell it. Or if you don't want to, you can write it this way. Sometimes it's written that way. El hospital. All right. Anyway, the L'Hopital rule is very easy to do. It just says you take the derivative on the top and on the bottom of the fraction. So this becomes this. Take the derivative on the top and on the bottom. 2x plus 2 over 2x minus 3. So this is the L'Hopital rule. You do the derivative on the top and the bottom. All right. Why didn't your teacher tell you this from the beginning? Why did they make you do this factoring business? I think because you didn't know what the derivative was at that time. And so what were they going to tell you how to do? But now that we know what the derivative is, this is the L'Hopital rule. And now you can plug the value in, and you actually get the answer. 2 times 1 plus 2 over 2 times 1 minus 3. This is 4 over negative 1, which is negative 4. And that is the correct answer. All right? This is the L'Hopital rule. It's very easy to do, and it is a great, like, to me, this is, I would rather do this than factor, right? And now this is a fairly easy factoring example, but I'm sure you all know, like, factoring in general can be much weirder looking, and I would basically always rather do this than factor the original thing, all right? There are some examples when really there is no alternative to doing the L'Hopital rule, or you could do something like lim x approaches 0 of sine x over x, right? If I just try to plug that in, I get sine 0 over 0, and sine of 0 is 0, so this is 0 over 0, all right? So you don't get an answer if you just try to plug in. But since I got 0 over 0, that means we can do L'Hopital's rule. We can do the L hop. This is, I'm taking the derivative on the top and the bottom. It becomes cosine x on the top and 1 on the bottom. And then you plug it in. Cosine of 0 is 1. So this is cosine 0 over 1, 1 over 1. It's 1, all right? This is an example which is, I mean, there is no other way to do this one. Like you can't factor on sine of x or anything like that, right? So the L'Hopital rule, it works great. It's pretty weird. Like why? I don't know if anybody ever wondered, but I'll just write down the rule. So the rule is, if plugging in gives 0 over 0, then I'll write it this way. Lim as x goes to a. I'm trying to write it in sort of a generic way here. It's always about a fraction in which, if you try to plug the number in, you get 0 over 0. And what the L'Hopital rule says is that this limit is the same as this limit. Rather than doing the original limit, we can instead take the derivative on the top and the bottom. Make sure you write those primes in there. They matter, right? I'm taking the derivative on the top and on the bottom. Can anybody say, maybe you're wondering at this point, don't we got to do the quotient rule if I have a fraction? Are you now telling me that we don't have to do the quotient rule? You can just do the derivative on the top and also on the bottom?
It's not that that's happening. It's you're taking the individual derivatives of each.
Right. But like, hasn't everybody always taught you when you have a fraction, you cannot take the derivative on the top and the bottom. You have to do the quotient rule. What's the, yeah?
I was thinking like since the bottom would also give you 0, so if you do g of x squared, which is the bottom of the quotient rule, you're still going to end up with 0, so you're still dividing by 0.
This is an interesting answer, but not quite what I wanted to hear. It's not wrong what you're saying, although there's a more fundamental reason why we don't actually want to do the quotient rule in this situation. I would say you should not be thinking about the quotient rule in this situation because I didn't ask you what's the derivative of this, f of x divided by g of x. That's what the quotient rule is used for. When I'm taking the derivative of a fraction, the answer is you do the quotient rule, right? But this is not the derivative of that. It's just the limit of this, which is actually completely different. And why does this equal this limit of these derivatives? That's another question entirely. So actually, next time I want to try and give you an idea of why this ought to be true. And then we'll do a bunch of examples. See you then.